All right, let's get started. Good afternoon, everybody. Welcome to Chem 170, Organic Chemistry, with your host, me, Dr. White. Now, a couple things I need to talk about. I don't know if I mentioned it or not, but a long while ago, I developed a method that helps eliminate test anxiety in students who have test anxiety and don't do good on tests. And I was thinking about it. Hold on one second. That's better. I was thinking about it, and this Wednesday after class on Zoom, I will go through the method. It takes about 10, 15 minutes for me to go through my whole teaching thing on how to learn the method. But over the years, students have been getting F's, D's, or C's, turn around and get A's. So it really works well, and I've seen it over and over again. So the one thing I will tell you, I will eliminate it from the video because once I tried before, I didn't have enough money to really advertise it. And I may try again in the future to try and sell it. So I'm not going to put it out free on YouTube. However, if you can't make it Wednesday to the class or afterward, come to my office hour and I'll teach you then. That's thirsty work. All right, another thing. I've been playing around with my cables and rewiring some stuff. Hopefully, I don't know if I did or not. Somebody had a question. Question, do I provide study guides? I call them reviews, and it goes over everything. We'll mention it now, and I'll mention it a lot more times. Every question on my exam, I've covered the concept behind that question at least twice, more than twice usually, but at least twice in lecture. I don't put any surprise. He never covered that. When I was a freshman at IIT, Illinois Institute of Technology, the physics lecturer we had was beyond awful. I'll let you put in your favorite adjective, beyond awful. And actually, I and a group of people got him fired. His test, he would find the little notes at the bottom of the chapter, and those are his test questions. And he usually never covered that in his lecture. I don't do that. It's not right. It's not fair. It's just not me. Hopefully that answers your question. All right, let's see, where was I going? Oh, I know. I'm going to be sending out the signature sheet again. Someone at the other school pointed out something legal that I really should protect myself, and also you should be aware of. And that is, when I'm recording things like that, your image is seen on here unless I minimize. I don't always minimize the pictures. And sometimes if you ask a question by turning off your mute or using your mic, your voice will be on the tape. And I don't know if you're familiar with the FERPA law, FERPA, and that gives certain rights to students. And in my new signature sheet, which I'll post sometime tomorrow, it says not only the first part you said, but you waive your FERPA rights. So if accidentally, and I try and keep it minimum, if your face or name gets in my video, which will be public, you won't sue me, which is a good thing. I don't want to be sued. All right, let's get started. First of all, the most important thing I can tell you to begin with, you should know how many bonds to carbon. Oops, how many bonds to carbon? 4. I'm ambidextrous. See, it's how many bonds I can do at the same time. Does this look like it's coming right at you? It's 4 bonds to carbon. If I were in a classroom, I'd go like this and tell you, look, my class is in 3D and you don't even have to wear the special glasses. I do bad humor both on the internet and in the classroom. But seriously, you should know there's 4 bonds to carbon. Now, another thing I'd like to ask you is, if you happen to be, since we last met, driving around and you happen to pass a gas station, did you think about alkanes? Gasoline, about half the weight of gasoline is alkanes. Did you see a candle? Did you think about half the weight of a candle is alkanes? Remember, when we're through with my lecture today and you look around, organic chemistry is everywhere. I stole that from SpongeBob. But anyways, it's everywhere. Use the one imagination, but I use organic chemistry is everywhere. And it won't hurt for you to think about it. Trust me, I'm an organic chemist. So if you happen to use some Vaseline or baby oil, or again, past the gas station, think about alkanes. Also, if you use your barbecue, think about alkanes. All right, another thing I wanted to mention is when we switched over officially this semester to mostly online courses or hybrid courses, whoever was teaching the course or the lead, I'm the only one teaching this, was asked to develop what's called the template for D2L for that course. And the school, the administration, had certain structure of that template using what's called modules. Normally, I don't use those in D2L, but to teach this class and also get some money for doing it, I did that. You know, you don't fight City Hall in certain things. So you'll see modules. And also because of that, I normally in D2L, and don't tell the dean, but next couple of days, I'll put it up anyways, I'd have a folder, lecture files, which I do, then I'd have problem set and problem set answers. And the dean said, no, you can't do that. You got to put that in the modules. So I did, and I forgot to upload. When I did that, I didn't attach them when I did it over the summer. So if you look at module 1, you'll see also in assignments, I didn't attach it, problem set 1, which is for chapter 2, alkanes. I will go through that this Wednesday. I won't go through the everything. It's sort of due Wednesday, but if you're a little late, I won't mind. But the reason I'm doing that is the dean was concerned with online. How do you keep the students on track? And that's why she wanted them in the modules. Normally, I don't do it where you don't have to hand it in, but to make the dean happy, which is always a good thing, especially if you want to teach and get paid, I did it. Now, to make her also happy, I made each answer or each problem set 1 point. Now, do you have to do all the problems? No. Just do 1 or 2 from each question, upload it, and I'll be happy and you'll get your 1 point. And since they're about, I'm guessing now 10 of them or 12 points, that could make a difference between an A and a B or B and a C. So it's in your best interest to do that. I'm glad, Freddie, you know you're not late. All right. Again, I'm still pretty new to Zoom. And when I'm talking, I don't always look at the chat. So always feel free to unmute your microphone and ask questions too. All right. Any questions so far? Remember, in my class, there's no such thing as a dumb question. And also time for commercial from Dr. White. Don't forget Monday and Wednesday night, JC, I'm sorry. JC, I'll answer your question in a second. On Monday and Wednesday nights, I have my office hours in Zoom from 6 to 7:30. If you have any questions, any concerns, or want to stop by and say hello to Dr. White, I'm available. Now, what I had originally, I think today, was uploading the signature sheet, but I'm going to be doing a slightly modified one, which I'll ask you to do again. Also, I didn't mention it, but because of some stuff I learned recently about, unfortunately, online cheating by students, not you, but I'm going to be putting an upload where I'll ask you to upload a picture ID with has your name and picture on it, either a driver's license, a state ID, or ECC ID. Take masking tape or something and black out important information. All I need to see is your name and your picture. And I'm not the only faculty doing that now. Guess what time it is? Time to get into some organic chemistry. Now, we finished the alkanes, and when it comes to functional groups or areas of organic chemistry, the alkanes are boring, except at the same time, they're probably the most important part of organic chemistry right now because of gasoline and oil and how it powers our society. But for a synthetic organic chemist, synthetic is the fancy word for making or to make. My training is making of molecules. Alkanes aren't that interesting. But now I get to get into a new area. In the coming weeks, I'll be teaching you different functional groups. Functional groups are a collection of atoms bond together in a certain way that can be in different molecules, but they always provide similar functionality to that molecule. Some of it physical properties, but more importantly, chemical properties, how that functional group reacts. And in the coming weeks, I'll be teaching a lot of different functional groups that are very important. If you look at your skin, it's made up of different functional group molecules. Same thing with what's left with my hair and the lenses of my glasses too. They're not real glass, they're plastic. All right, it's time to start your journey into or really organic chemistry. What I will be doing is, first of all, introducing you to functional group the next number of chapters, showing you where you find it in nature, because that or in our daily life, excuse me. And then I'll show you how to name it, how to draw its structures, and then the real fun part, the chemistry of that functional group. Let's begin. Oh, got a frog in there because I haven't talked all weekend probably. I know last week we had a clicking or chirping sound. Let me know if you hear it again. I did some recabling, tried to minimize it. Hopefully I got rid of it, but who knows? Or it could be something with Zoom or my internet. I lost internet this morning for an hour, which that's the first time in over a year and a half that happened. All right, let's get started. All right, let me check. Remember my thumbs up, people. You see chapter 3 on the screen? Give me a thumbs up. Thank you. I hate to do this, but Zoom has a problem. I think I've put it up there and students say, I can't see anything. All right, this new chapter deals with alkenes and alkynes. What's an alkene? It's a carbon, hydrocarbon. Remember, a hydrocarbon is molecules with only carbon, hydrogen atoms that contains a carbon-carbon double bond. And we'll be drawing double bonds like this. These two lines tell you it's a double bond. And remember, there are 4 bonds to carbon. So this carbon has 2 more bonds here. This one, same thing. I'm drawing this a certain way. I'll teach you why later today. But this is a double bond. Remember, each line is a pair of electrons. Whoa, why did it do that? That's abbreviation for electrons. Now, I'll never ask on a test, but I know some entrance exams have asked, if you have a double bond, you have 5 carbons, how many hydrogen? The formula for that is CnH2n. Hold on one second. And that's the formula for a molecule with a double bond, also for a ring too, but let's not get, but anyways, I will never ask that on a test. So an alkene is a hydrocarbon molecule with only hydrocarbons to hydrogen that has at least one carbon-carbon double bond. Now, the other functional group, and we teach these together, is an alkyne, or also plural, the alkynes. That also is a hydrocarbon, and that's a molecule with only carbon-hydrogen atoms. That's what a hydrocarbon is. And that contains a carbon-carbon triple bond. And here we have a triple bond. One line is a single bond, 2 lines double bond. I hope you all can count. That's part of the class requirement. You have to know how to count up to 10 at this point. And you see 3 lines, and that's a triple bond. Now, again, I'll never ask on a test, but the formula for alkynes are CnH2n minus 2. So alkene, double bond, alkyne, triple bond. Now, one of the neat things about my class, you can ask, why am I learning this stuff? The obvious answer is someone told you have to take this class and you want to get a good grade so you can get into a program or a school, like nursing school, and that's why you're taking this. But really, why should you learn this? You're going to find out this semester. And you should always ask that question besides your grade, why am I learning this? Well, let's talk about double bonds. How many of you are familiar with, and I'm going to get into stuff you never thought Dr. White could get into in this class, but let's talk about carrots. Carrots, yeah. I think I'm going to assume each and every one of you have seen a carrot in your life. I hope you have. And if you go to the supermarket in the vegetable area, by the way, one summer, Dr. White worked produce basement at a monster supermarket in Chicago, so I do know my produce quite well. But it was so big, we used to send up 50 cases of lettuce an hour on Saturday. That's how quickly it was sold in that supermarket. But anyways, carrot, orange, I think you're all familiar with that. And let's look at something. What makes the carrot orange? Turns out it's an organic molecule. Called beta carotene. And hopefully you all see on your screen beta carotene. And here's the structure. Do not write it down. I don't expect you to learn it, but this is the line method. Every bend in a line is a carbon. Every end in a line is a carbon. Like these are methyl groups. Here we have a ring. Here we have another ring. Notice all these carbons, and each 2 lines is a double bond. And beta carotene has a lot of double bonds. And this is the molecule in carrots that gives it that color, the orange. And that's because these double bonds are conjugated and can absorb light. All the colors of the rainbow except the ones mixed together to give orange. Now, it turns out right around here, your body can break this molecule in half to make a new molecule called retinal. Retinal. Ooh, it's something your retinas you use for your eyes. And I think you've all heard carrots make you see better. Well, there's a sort of a little truth to that because your body breaks down the beta carotene for chemicals for your eyesight, which is why Bugs Bunny can see so well. You people all know about Bugs Bunny, don't you? Hope I didn't just do a generation gap. Now, let's continue. Well, if I'm in the produce area, let's talk about tomatoes. I think you've all seen red tomatoes. And give me a second while I look it up. And hopefully you see this long molecule. Every bend in the line is a carbon. Every end of the line, like here, here, and here, are methyl groups. If you notice 2 lines, these are all these double bonds. And lycopene is similar but different to beta carotene. And when this absorbs light, which is in the tomato, of a ripe tomato, it absorbs all the light except the color red. And that's why tomatoes are red. So the next time you're with some friends, neighbors, or loved ones, and you're having a salad with them, and it's got carrots and tomatoes in there, you can tell, oh, you know, the carrots are that color because of a molecule with a double bond, an alkene, and the tomatoes are that color because there's a molecule with double bonds in it that make it red. Don't. You'll lose friends real quick, or people won't invite you to dinner or lunch. But Mother Nature, the greatest of all organic chemists, uses alkenes, double bonds, in your daily life. There are more examples we'll get through during the semester. Now, both alkenes and alkynes are called unsaturated hydrocarbons. As you learn, an unsaturated hydrocarbon is a molecule that has only carbon and hydrogen and at least a carbon-carbon double or triple bond. Now, we call it unsaturated because it's not fully saturated with hydrogens, which you'll learn later this chapter why. And again, it consists of 1 or more double or triple bonds. The addition of hydrogen gas, which I'll teach you, converts an alkene or alkyne into an alkane. I'll never ask this on a test, but you'll see it later on. This slide I forgot to take out, ignore. Now, let's talk about nomenclature. First of all, quick commercial from Dr. White. Hopefully you've all learned this chart. If not, this is a good week to learn it because you're not going to learn it the week before test 1. And if you don't know this chart, you just lost 50 points on test number 1. And that's the IUPAC names for the alkanes: methane, 1 carbon, pentane, 5, decane, 10. Now, it turns out we use these names to name other compounds. Notice at the very end of each one of these, there's ANE. Now, for alkenes, the ending is ENE, and it's used to designate a carbon-carbon double bond. We won't do more than 1, which is diene. I'm not going to do that in here. YNE is used for a triple bond. Forget about diene either, or diene. Now, how do you do this? And I'm going to go through this. I'm going to read it first, then we'll practice it, because you by now know Dr. White. We'll do that. All right. First of all, you select the longest carbon chain And here's something different that contains both carbons of the double or triple bond. Number that chain from the end of the nearest multiple bond so the carbon atoms have the lowest numbers. You indicate the position of that number of the first carbon with the lowest number. And I'll show you this all, because when you read it in the abstract, it doesn't make sense. All right, one thing I'm missing here, and I'll do right now. Everybody see the whiteboard, this white screen? Thank you. All right, let's look at a molecule. And from now on, when you look at a molecule, you should look what's different. What's not a carbon-carbon single bond? What's not a carbon or hydrogen? Because that's where all the fun is. That's where everything's going to happen. So from now on, whenever you look at any organic molecule, and this will be true the whole semester, and this is what I do every time I look at a new molecule, I look for what's different. What's not a carbon-carbon single bond, one line between carbons, and what's not carbon-hydrogen bond, because that's where the fun is. So if we look here, oh, look, something different, a double bond. So this is an alkene. How do you name it? First of all, you have to count how many carbons in the longest chain. There's only one, with both carbons of the double bond, and that's 4. Now, for double bonds, you take butane and it had ANE, you drop the ANE and replace it with ENE, butane. Now, you mark which carbon of the double bond is the smallest and use that in the name. I hope you all admit 1 is less than 2, and therefore this would be 1-butene. And I'm done, because there's nothing else. Let me point out, notice this carbon has 2 hydrogens because it has 2 bonds, and 4 minus 2, because you all know there are 4 bonds to carbon, is 2. This carbon only has 1 hydrogen because you have 1, 2, 3 bonds, and there's always 4 bonds to carbon. 4 minus 3 is 1, and that's why. Now, why don't you try this carbon? First, how many carbons in the longest chain? I see a question. Yes, Freddie, may I have a good class? And JC, I don't think if it was due today, you can resubmit it. Other than labs being super late and tests, I'm pretty laid back, especially now with COVID-19 and the various things that could do if you had to work extra or whatever to your schedule. All right, why don't you try naming this? Find the longest chain, name it as an alkane, drop the ANE ending, add ENE, and don't forget to put a number. This is a nice Dr. White shears. When you're done, give me a thumbs up or your symbol. All right, I think everybody's done. Let's do this. First of all, look for what's different. What's not a carbon-carbon single bond? Oh, look, it's a double bond. So this is an alkane. This you don't have to put down, but I will. And an alkene has the ENE ending. How many carbons in the longest chain with the double bond? Both carbons. And hopefully you've learned 6 is hexane. Now, ANE you drop and replace it with ENE, hexene. That tells you have a double bond. Now, what's the lead carbon closest to the end of both carbons double bond? This one, that's carbon 1. So this would be 1-hexene. Oh, let's do one more. Remember, you do alkyl groups. Just like you have in the past. And why don't you try this one? How would you draw this or give the IUPAC name for this molecule? Remember, look for what's different. I always do. Normally, if we're in class, I'd have a copy of the alkanes and the alkyl groups table in front, but it's hard doing Zoom. Hopefully you have that written out or printed out. And if you have anybody extra watching this along with you, I won't even charge extra. Nah, it's $19.95 plus shipping and handling. No, I'm just kidding. All right, I think anybody need more time? Going once, twice. All right, let's do this. Remember, always feel free to say, yes, I do need more time. All right, first of all, look at this molecule. What's different? Oh, look, double bond, 2 lines. How many carbons are in the longest chain double bond? I don't know. 1, 2, 3, 4, 5, 6, 7. Next, I could have also said 1, 2, 3, 4, 5, 6. And I hope you all agree 7 is longer than 6. So what is 7-alkane? And that's heptane. But the ANE you drop and replace it with ENE for double bond, heptene. Now, if I number it the way I have it up here, you'll see the lead carbon closest to the end with the lowest number would be 1. And the question is, am I done? And the answer is no. Because when I say 1-heptene, that's spoken for. And look what's left over. It's your old friend to be, the methyl group. And that's an alkyl group or substituent. What carbon is it on? Carbon 5. So this would be 5-methyl 1-heptene. And that's how you do nomenclature one type. There are two types of nomenclature questions or skills you should have as an organic chemist, which means there's two types. Shh, don't tell them giving this away. Two types of nomenclature question I can put on an exam. One is, here's the structure, give the IUPAC name. The other is, here's the name, draw the structure. Someone asked, could it be 3-methyl-6-heptene? Let's take a look at that. It's a good question. Now, IUPAC rules are, and let me do it in green, blue. Notice the lead carbon here, the double bond closest to the end you started counting, is 6. If we go this way numbering, in red, the lead carbon is this one, 1. And IUPAC rules are functional group carbons always get the lowest number. So the right way to number it would be 1, the way I have it. And if you do it, then the methyl is 5. The way you asked would give the carbons of the double bond higher numbers, which is not following the IUPAC rules. And if you do that, the IUPAC police will come and arrest you. No, there are no IUPAC rules. So hopefully that answers your question.
Hold on. I counted the bonds instead of the carbons because I wasn't thinking. But could it be 3-methyl-7-heptane then?
No.
No? Okay.
You always want the double bond carbons to have the lowest numbers. That's, hi, what's your cat's name?
It's Peaky.
Hi. Anyways, I won't charge him or her extra either. Anyways, IUPAC rules are devised so two different molecules never ever have the same name. And part of those rules to have that happen, I know of no exception where two IUPAC molecules that have the same, they're different but with the same name, you always make the carbon atom or atoms of a functional group, in this case double bond, the lowest numbers. You have two ways. One, the lead carbon will be 6, the other is 1. You always pick the lower number for those carbons, which would be 1. And that's just the rules. And because of those rules, it works. Does that help?
Okay. Yes, thank you.
You're welcome. Remember, all questions are good questions because I know this stuff. I've been doing it a few more months than you have, a few more decades, a few more half centuries. I should have shut up. I was ahead. But ask questions. It's all new to you. All right. So there are two types of skills for naming molecules, nomenclature. One is, here's the structure, give the name. The other is, here's the name, decode it. Remember, it's a magic secret code to figure out what's the structure. Let's do that. Now the question would be 3 points each. And say this were A. And you have to draw the structure for 1-pentene. How do you do this? All organic chemical names, you start from the right and move left. And as soon as you see the ending ENE, you know that's a double bond. If this were ANE, that would be 5 carbons. So you now know you have 5 carbons. Hopefully you all see me write this. If not, someone scream or something, yell at me, you can't see it. I assume you can all see it. And now, most of you are going to call this carbon 1. Therefore, I have a double bond. Now, you could have started the other way. And either way is correct. Call that 1. Now, remember, there are 4 bonds to carbon. You have to put the hydrogens in. There are 2 bonds to this carbon, 4 minus 2, 2 hydrogens. To this carbon, there are 3 bonds. 4 minus 3, 1. This one has 2 bonds. Same thing here, same thing here. Going the other way, we have 2 bonds. Therefore, 4 minus 2 is 2. Remember, there are 4 bonds to carbon. This one has 3, 4 minus 3, 1. Therefore, it's got 1 hydrogen. And I'll put in the rest because we worked on that last week. And which is correct? Let's call it A circle or B circle. And the answer is both are. Either way, all you're doing is rotating the molecule 180 degrees. Here's my left hand. If I say, close your eyes, while your eyes are closed, oh, look, something different. You say, no, you just rotate your hand. Molecules are not stuck on a piece of paper. They move around. Now, before we go further, has anybody heard the clicking sounds? Or are they pretty much gone right now? I guess they're gone. I better keep my mouth shut. All right, let's do one. Let's have you do one. Why don't you draw, and this would be, say, part B if you saw it on test, draw the structure for 1-octene. And while you're drawing, I just had a good thought. Tomorrow's beginning of September. That means there's only a couple more weeks until the Bundesliga starts again. For those who don't know what the Bundesliga is, it's the German soccer league. Dr. White is a München fan, Bayern München. München is the correct way for saying the German city, Munich. And yes, I've been in Munich. I worked in Germany, worked in a lot of countries. All right, I see a bunch of questions. Let me stop share so I can pull this up. Come on, chat. It comes and goes, and I have no idea why it's doing that. I'm going to check with Zoom and see if they can't help me. Is it doing it more now or staying the same? Is it gone? If it's gone, hold your thumb up. If it's not, down. All right. I don't know what's happening. It's the computer gods are mad at me. But anyways, let's go back to our molecule or drawing it. All right. How do you know what to draw? You look at the molecule's name and you start this way from right to left. Always go right to left. And look at the end. En, the ending tells you double bond. If this were ANE, that would be octane. Octane is 8 carbons. I better get to work. I have 8 carbons. And now, where's the double bond? Carbon 1. And you could have also put it this way. Most of you are probably going to put it on that side. And now I'll put in the hydrogens. Remember, there are 4 bonds to carbon. And also remember, it's your responsibility. If I make a mistake, let me know, because I'm going at warp speed. For those who know science fiction, that means as fast as I can. And this is how you do it. And if we had an alkyl group on, oh, let's do one. And why don't you draw the structure for 3-methyl-1-pentene? Go. While you're doing that quick commercial, remember on Wednesday after class, and I'll mention it after the break, we'll end early on Wednesday, and I'll explain why after the break. I will teach for those who want to stick around how to eliminate test anxiety. Free of charge. Actually, it's not free because you have to pay to get in my class. Don't forget, when you're driving around, if you see a gas station, think about alkanes. Anybody need more time? If you do, give me a thumbs up. Nope. All right. Let's do this. How do we decode this secret message to figure out what to draw? You start from the right and move left. EN, the ending, double bond. If this were ANE, pentane, 5 carbons. So I have 5 carbons. My double bond is at carbon 1. I'll do it this side. So this is 1, 2, 3, 4, 5. On carbon 3, there's a methyl group because I'm going this way. Methyl on carbon 3. And now I'll put in my hydrogens. And that would be 3-methyl, 1, 2, 3, 4, 5 at carbon 1, 3-methyl, 1-pentene. Remember, EN ending tells you double bond. And don't forget, you should always remember there's 4 bonds to carbon. You gotta train this finger, it likes to do this. I think it really wants to do this. For those who don't know, that's the Vulcan greeting from Star Trek, which came from, if you go to a temple, Jewish temple, at the end of the service, the rabbi will give the benediction and hold his hands out like this. This is the Hebrew word shin for shalom, and do the benediction, which is how Nimoy remembered when he was a boy. He remembered that. I'll make that the Vulcan greeting. That won't be on the test. With that, it's time for a break. I'll see you at 5 minutes. I'm going to go stretch. and come back in 5, and we'll continue our journey into alkenes and alkynes. All right, let's get back to work. Hope you all had a nice break. I got to stretch. After sitting for an hour or 50 minutes, if I don't, my legs start cramping up. It happens when your hair turns gray. At least it happens to me. All right, let's get back to work. Come on, screen share. All right, there's some common names I thought you'd be familiar. One of them you should know. The others, I just thought I'd just show you them. And let me just check. Everybody see the screen with ethylene on there? Thank you. All right. Ethylene, there are common names that were developed long before IUPAC, and people still use this. Ethylene is the simplest common name for the simplest alkene, which we would call ethene, but it's called, most people call it in the chemical industry, ethylene. Propylene would be this alkene. These two, not on test. But this last one, acetylene, is the simplest triple bond. You can draw it this way. Now, this is called on this end a left justified hydrogen. You can also do it, my software likes to do it this way better. Yes, I have special software to draw structures. Either way is correct. This is acetylene. Dr. White's going to be subtle. And you should know the structure of acetylene. If on a test I asked you draw the structure of acetylene, you should know to draw this. Now, one thing, have you ever heard the term acetylene? Some of you might have. Let's talk about it. Have you ever seen a movie or been to a body shop where they have that real hot torch that will melt metal? Or you see in the movies, it cuts the center out of a safe so they can break into it? Well, they're using an acetylene torch. When acetylene with a triple bond, triple bond, burns, it gives off a lot more heat than methane does with no triple bond, like when you cook with. And because it's a much hotter flame, it does what you see like in a movie, melts metal. And those are called acetylene torches because they burn oxygen with acetylene. Now, one which I won't ask you to learn, but a substituent. When you have a double bond in a substituent attached to a ring or a long chain, we call that a vinyl group. Where have I heard that name vinyl? This won't be on the test, but I thought I'd mention it because I'll talk about it later. Where have I heard vinyl? Why am I thinking about floors? Vinyl floors. And those are made from material that has vinyl groups in it. For those of you who are old enough, when I was in high school, the rage were for all my parents and my friends' parents was all the furniture in the living room. So it would be protected. They had what was called vinyl slip covers, which I hated because you sat on them and you stuck to them, especially in the summer. And it hurt getting your arm off them. But all my friends of mine, they were called vinyl covers because the material, the plastic for that went over your parts of your couch or chairs in your living room were made from molecules that had vinyl groups. A lot of organic chemical names are in our daily life names. You just don't know about it yet. You will. All right, let's talk about double bond. And before I do this, click. Will this slide, next couple be on the test? No. I turn the switch, click off. Will it be on the test? But it's good background information to understand when I do talk about something you need to know. And that's the pi bond. This you should know, and I'll talk about it over and over again. A double bond is made up of a pi bond and a sigma bond, and this you should know. The rest of it I'm not going to cover it on the test ever. It's abbreviated by the symbol pi, as you see there. And don't worry about this. It contains 2 sp squared hybridized orbitals, 1 p orbital. The bond angle, which I won't ask on a test, but you'll see why I draw it a certain way, which I haven't yet, is 120 degrees. And there's no rotation around a carbon-carbon double bond due to p orbital overlap of the pi bond. And normally you draw a double bond this way. These lines go to other carbons or hydrogens. And this bond angle is 120. Same thing here, 120. And this is rigid. A carbon-carbon single bond, there's rotation around the single bond, just like on a fan. But here, this is fixed. Unfortunately, because I haven't been in ECC since March, I don't have my models. And when I was thinking about it about last week, I contacted someone who was going there this week. They're going to send me some, and you would see a double bond is fixed. But for now, you'll just have to believe me. Now, what does a carbon double bond look like? The switch is off for this slide. You have 3, that's these in yellow, sp2 hybridized or single bonds, and this blue, or turquoise blue, my sisters always say, I don't know my colors, and they're right, some of it. But anyways, this is called a p bond, and it has this orbital, the sp2 120. Now, when you bring 2 carbons together to form a carbon-carbon double bond, this again switches off. First, you have overlap here of the electron here and here to form a sigma bond. Then the p orbitals overlap to form the double bond. Here we have 2 electrons. Anywhere where it's blue, if I could stop time, I'd find those 2 electrons. The sigma has 2 electrons, and anywhere here, if I could stop time, you'd find those 2 electrons in that area. And this is your double bond. And this you should know, because I'll say it often enough. Double bond has 1 pi bond and 1 sigma bond. And this is what it looks like if you were to look at it at the atomic or electron scale. Now, because of that, this holds this from rotating. This will not rotate. Therefore, these 2 bonds and these are flat in this plane. And that plays an important role in many things. And as I show here, switch is still off. The double bond is trigonal planar. Trigonal, this is a triangle, and it's flat, and the plane is planar. And you can't have rotation. I'll teach you later on. How many of you have heard, well, I'll get to that in a little while. That double bond plays an important role in our daily life. Really? Yes, really. And you'll learn. Let's go back now. You know how to really draw organic molecules. Let's do a double bond or two, draw a molecule, and get the IUPAC name. Remember, IUPAC did such a great job, and I'm being totally sincere and serious, that no two different molecules ever have the same name. Two different molecules, always, always, no exception, because they did such a great job, always have different names. So let's take a look and try a couple. And now I'm showing the stereochemistry, how it looks really in 3D of a double bond. Let's do two. And remember, IUPAC has done such a great job of making up the rules that no two different molecules, let's call this A, and let's call this B, because we don't know their names yet. Now, let's look at A. How many carbons in the longest chain? Now, even though there's a bond angle here, this carbon is bonded to this carbon, is bonded to this carbon, is bonded to that carbon. So this would be 1, 2, 3, 4. What's different? Double bond. So I know, oh, it's an alkane, and therefore, what do I have? 4 carbons, butane. But I'm going to drop the ANE and put in ENE, butene. Now, if we count this way, 1, 2, lead carbon is 2. If we started 1, 2, 3, 4, the lead carbon still would be 2. So this is 2-butene. Let's go over and do this one. What's the longest chain? 1, 2, 3, 4. Even though these are bent like this, just like a chain you can bend different ways, it's still linked together. This has 4 carbons. Oh, I know what 4 carbons is. Butane. But for a double bond, you drop the ANE ending and put in ENE ending. And now if I look at B, how many carbons? 4. If I number this way, the double bond starts at 2. If I start this way, double bond starts at 2. So this would be 2-butane. Uh-oh, we got a problem. This molecule and this one are clearly different. You can't superimpose them or rotate, but they have the same name. Oh no, what do we do? Relax. IUPAC knew about this and came up with special rules. And those special rules are two days later, cis-trans isomerism. Isomers mean two different molecules that have the same number of carbons and hydrogen, but are connected differently. And cis and trans, I'll explain. Due to no rotation around a carbon-carbon bond, you can have cis, which is 2 groups on the same side for 2 groups on the carbons of double bond, either hydrogen or groups. Trans is when they're on opposite sides, 2 groups or atoms. So let's go back to our diagram. And notice, if I were to use my finger in class, I'd show you with a pencil, but here's my plane. Let me do it in red. And notice these two methyl groups are on opposite sides of this red line. Same thing with the hydrogens. And when things are on opposite sides in double bond, we call that trans. So the correct IUPAC name would be trans-2-butene. Now, if we look at the other molecule B, and I put in that same plane, it's really like if you put your hand there or a pen, laid it on here. Notice these two methyl groups are on the same side of this line, or the hydrogens are on the same side. And that's called cis. And therefore, this would be cis-2-butene. So, opposite side, trans, same side, cis. Now, when you have two of the same atom or group on the same atom of a double bond, you have neither cis or trans, because you can't. Let's take a look at this. Now, when we started out naming it, did you notice all the double bonds started with one? There was a reason. I didn't want to talk about cis or trans. Now, showing bond angles, this would be 1-butene, which we did. 1, 2, 3, 4. Double bond. Now, is it cis or trans? Well, if I had my same plane or line, oh, look, I have a hydrogen opposite. That's trans. No, I have a hydrogen and it's on the same side of this. That's cis. Well, it can't be both, therefore it's neither. So in this case, when you have two hydrogens on the same carbon double bond, or let's try one on your own. Well, let's do cis and trans first. And the question is 3 points each. What's the IUPAC name for this molecule? And how do we do that? I'll do one more. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6. 6 carbons is hexane, but it's a double bond, therefore it's hexene. Where is the double bond? Again, you count from the side closest to the end and give those carbons lowest. Either way, 1, 2, 3, or 1, 2, 3 is 3 hexene, but I'm not done. If I put in this line, notice the hydrogens are opposite, or this alkyl group and this group, it's not really an alkyl group, those two carbons, those two, opposite is trans. So that would be trans 3 hexene. And now I've got to share the fun. Otherwise, that'd be cruel, unusual punishment. And why don't you try this one? What would be the IUPAC name for the following? Psst, you're doing serious organic chemistry. Hopefully it isn't painful. If we were in class, I could look around and say, when you're done, look up and smile. But since I really can't do that because some of you don't have webcams or don't have them turned on, give me a thumbs up. I see some already are done. Remember, this is all new, so if you're having trouble, that's okay. I'm here to help. Give you another 10.6 seconds. 9.2, 9.3, 9.5, done. All right, let's take a look at this molecule. Look at what's different. What's not a carbon-carbon single bond or carbon or hydrogen double bond. Alkene. How many carbons in the longest chain with the double bond? 1, 2, 3, 4, 5, 6, 7. 7 is heptane. If it was an alkane, but it's an alkene, drop the ane ending and put in ene. Where is the double bond? The carbon closest to the end of the, well, in the double bond, and notice it's on carbon 2. If we started the other way counting, this would be 1, 2, 3, 4, 5. And I hope we all agree 2 is smaller than 5. Therefore, we have this. And the last question is, do we have cis-trans isomerism? And notice I have a hydrogen here and here. And if I put in my plane, if we were at ECC, you'd see my hand on the board as the plane or a pencil, or my pen, I'm writing on the whiteboard. And notice the hydrogens are on the same side, or this group and this group are on the same side, but it's really 2 of the same atom. And therefore, same side is cis. So this would be cis-2-heptene. Now, when it comes to a ring, something like this, notice I have a double bond. Oh, wrong pen. And send a ring. Unless you get up to, and I forgot how large the ring has to be, 16 or 18 carbons. In rings, all double bonds are cis until you get to large, which most people don't. Since everybody knows that, you don't put it in there. Now, in a ring, one of the carbons when you have no other functional groups in this class most of the semester, that would be true. If you're getting a PhD or a chem major, it wouldn't be true. One of the carbons in a ring, double bond, is always number 1. And if there's nothing else in there, you don't have to number it because everybody knows one of these carbons is number 1. So how do we name this? Well, it's a ring, 6 carbons. It would be, and it's a ring, cyclo. Dr. White remembered to put the cyclo in. Hexane. But just like in an alkane, cycloalkane, drop the ane ending, put in ene. Since we know one of these is going to be number 1, I don't have to put a number. I'm done. And that's how you do a ring without an alkyl group. Now I have to teach, well, let's you try one. What would be the IUPAC name of this molecule? Go. While you're doing that, those who are interested in helping me out, do you still hear that cricket or chirping noise? Give a thumbs down. If you don't, do a thumbs up. Could you do that for me? Nobody wants to do that. If you can't hear me, go, oh no. All right, looks like things are, Dr. White has a sense of humor and I use it. All right, I think everybody's just about done. Let's do this. What do? I look at the molecule and say, what's different? What's not a carbon-carbon single bond or carbon-hydrogen? Ooh, double bond. It's in a ring. There's 1, 2, 3, 4, 5 carbons. Every bend in a ring is a carbon. That's cyclopentane, cyclo ring. Pentane for 5 carbons. But since it's an alkene, ene ending, I drop the ane and put in ene. There's nothing else in there. I know one of these are going to be carbon 1. I don't have to put that. I'm done. Cyclopentane. Now, let's look at what happens when there's something on the ring. And the question is, what's the IUPAC name for this compound? And first you look, what's different? What's not a carbon-carbon single bond or carbon-hydrogen bond? Oh, look, a double bond. That's just screaming at me, I'm different, and I saw it. And it's in a ring, there's 6 carbons, and that would be cyclopentane, cyclohexane, I'm sorry. My brain was on the last molecule. But you have a double bond, this ane ending and cyclohexane is replaced by ene. Now watch carefully. One of these 2 carbons has to be 1, the other has to be 2, when there are no other functional groups, which is true in this ring. And you number it, so also the alkyl group gets the lowest number. So if we start here, this is 1, 2, 3. Now watch closely because this is a common mistake students make. They'll say this is 1 and try and make this 2. No, the other carbon, if you call this 1, this has to be 2, 3, 4, 5, 6. So now you don't have to put the number, but you have a choice. Is this 3 or 6? And you always pick the lowest number. 2 carbons, ethyl group, and it's on carbon 3. And that's important. Let me go through this again. because this is something that trips up students. In a double bond, one of the carbons of the double bond has to be 1, the other 2. And then you try and number it so the alkyl groups have the lowest numbers too. And if I go in blue and if I call this carbon 1, this is 2, the ethyl group is on carbon 3. If I call this carbon in red right here, number 1, then this has to be 2, not this one, because one has to be 1, the other has to be 2, and then 3, 4, 5, 6. And the correct way, 3-ethyl cyclohexene. And why don't you try this one for your enjoyment? What would be the IUPAC name for this molecule? In case you haven't learned it, this right here is called an isopropyl group. Hopefully you'll be learning that chart if you haven't already. And if you're with someone, make them work on the problems too. No, you don't have to. I guess you're getting a 2-for-1 sale. This one's tough. For those who finished early, please be patient. I try and give everybody time to do it. When you're done, give me a thumbs up. All right, I think everybody's done. Let's do this. All right. Now, if we look at this, we say, what's different? Oh, look, a double bond, and it's in a ring. How many carbons? 1, 2, 3, 4, 5. Pentane, ring, cyclopentane. Double bond, cyclopentene. Remember, cyclo, pentane for no double bond, but you drop the A and E ending, put in ENE for a double bond, cyclopentene. This is an isopropyl group. I'll write it down here because I'm running out of room. That's a Y. And now let's take a look at this. There's 2 ways you can consider numbering it. This is 1, this is 2, this would be 3. Remember, one of the carbons double bond has to be 1, the other 2. If I go the other way, 1, 2, 3, 4, 5, and the alkyl groups always you number in such a way to give the lowest number. Now you got to use your high-level math skills, which is lower, 3 or 5. Time's up. Hopefully I'll pick 3. And this would be 3-isopropyl cyclopentane. Isn't it amazing all the neat stuff you're learning? You can say yes. Remember, unbiased. I'm an organic chemist. Now, there are two types of nomenclature question in organic chemistry. And one is, here's the structure, give the name. The other is draw the structure from the name. Now, we did it earlier with double bonds, but not with cis and trans or rings. So let's have some fun. If I say fun enough, you'll really believe it's fun, and it works. And the question would be, draw trans 3-nonene. This one I'll do. How do you decode this to know what to draw? Start from the right and move left. And the first thing you see is the ENE ending, and that's a double bond. If this were ANE, nonane is 9 carbons, so I better get to work. But first, before I do that, I'm going to look at this and say double bond where 3, and it's trans. So I'm going to do 1, 2, 3. This shows a 120-degree bond angle, double bond. Now, what's trans? Opposite sides. Therefore, the hydrogen will be opposite sides, 3, 4, 5, 6, 7, 8, 9. 4 plus 5, 9. And now I'll put in the hydrogens. And notice if I were to count 1, 2, 3, it's 3, double bond, 9 carbons, nonene. And then notice the hydrogens are on opposite side of a plane going like this. And that's trans. And that's how you do it. Now, cis would have been on the same side. And why don't you try this one? Why don't you draw cis to octane? Oh, my Adobe Creative Cloud just let me know I have 4 updates. You can wait, Adobe Cloud. I don't know if you heard that or not. I'll go peek at your videos and see if you're done yet. Dr. White's peeking. If we were in a classroom, I'd be scanning the classroom, seeing how many people aren't done yet. So everybody would have enough time to finish. Did you spell it right, Alejandro? Quick, check again. Aren't you glad I have a sense of humor and use it? I am. Can you imagine today I'm going to speak about double bonds. This is double, nah, we're going to have fun with double bonds. We are. All right, let's get to work, Dr. White. Okay. And the question is, how do you name this? How do you decode this? You always start from the right and move left. All organic names are like that. EN, the ending, tells you double bond. If this were ANE, octane, 8 carbons. Notice double bond is on carbon 2 and it's cis. So I'll do 1. Now, 2. The hydrogens will be on the same side. There are 2 ways you can draw it. I drew it this way. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Did it right. Put in my hydrogens. Remember, there's 4 bonds to carbon. That's a 3 if you can't see it. And notice I have 1 through 8, octane, double bond, octene, carbon 2, 2 octene, and these hydrogens are on the same side of a plane or that dotted line, so that's cis 2 octene. Oh, let's do one more. And why don't you try drawing 5-methyl trans 3-decene. Start working. Now, I should warn you, we're doing nomenclature, which is not the most exciting. After this chapter, nomenclature will get quicker and other fun stuff will get longer. And that's a promise from Dr. White. Just think, tomorrow you can surprise your friends when you talk to them about, you know what an alkene is? Nah, don't. Unless they happen to be watching with you. Quick commercial from Dr. White. Remember, Wednesday after class on Zoom, I'll stick around and teach those who want to stick around the method to eliminate test anxiety like that. And it works real good. And when you're done, don't forget to smile or give me a thumbs up if your video isn't on. Or if your video is on, you can do a thumbs up. See, people are just about, the final hydrogens looks like they just went down. Anybody need more time? Going once, twice? All right, let's do this. How do you decode this to know what it is? All organic molecules, you start from the right, move left. ENE ending, double bond. If this were ANE, it would be decane, 10 carbons. So I better get, and notice we have double bond, carbon 3, and it's trans. 1, 2. I'm going to show my double bond with the bond angle. Now, trans means the hydrogens are opposite, and then 6 more carbons. Now, on carbon 5, there's a methyl group, CH3. 1, 2, 3, 4, 5. And now I know there are 4 bonds to carbon, so I can put in my hydrogens. And let's take a look at this. 4 plus 6 is 10. I have my double bond at carbon number 3. It's trans. How do I know? If I put in my plane, the hydrogens are opposite, and I have my methyl group on carbon 5. So that's how you do 5-methyl trans 3-decene. Isn't it amazing all the stuff you're learning? Now, let's do this one. I'll do this one because I see our time's almost up. If we look at this, how do you draw this? Start from the right, go left, ENE ending, double bond, cyclohex, if this were ANE, cyclohexane is a ring with a double bond, 6-membered ring. You can put double bond anywhere. I'm going to do that there. You could have put it between any 2 carbons on here. Then I have a T-butyl group, which I didn't spell right. Now I fixed it. And it's on carbon. Ooh, what do we do? Well, 1 of the carbons double bond is always 1. So I can call this one 1 or this one 1. I'll call this one. I'll put in my T-butyl group, which is one of Dr. White's favorite alkyl groups. Each one of these carbons is CH3, and I'm done. And if I look at the clock, it's just about almost time. Now, here's the thing. When you have a ring, remember 1 of the carbons is 1, the other one is 2. And notice since I have the T-butyl group on carbon 1, doesn't matter which one of these I did, because it would be the same. With that, my legs are telling me it's time to stretch. So I'll see you in 5 minutes, and we're on the home stretch. All right, ring, 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 ring. Let's get back to class. You know, the old school marm with her bell. Ring, 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 ring. That's one thing I don't have, a bell, but I have this. I love that. Company that made those is no longer in business. I have 3 of them, and I treat them like gold. All right, we were talking about how do you draw an alkene by its name. Hang in there, nomenclature is not the most exciting, but it is quite important. And let me give you a couple. And why don't you draw 3N-propyl cyclohexene? Are crickets back or are they gone right now? Thumbs up, they're gone. Thumbs down, they're back. Oh, good. I have no idea how, all summer we didn't have that problem and all of a sudden now, well, I do have a new webcam. I was using an older HP and I finally got my hands on a Logitech. They are hard to come by. All right, I think everybody's done. Let's do this. And the question is, draw the structure for the following molecule, 3-point-C. You start from the right and you move left. E-N-E ending, double bond. Ooh, cyclo, ring. Hexane, if this were A-N-E, would be 6-membered ring. I'll put the double bond here for now. You could put it between any 2 carbons. All you're just doing is rotating the ring. And if I call this 1, this is 2, this is 3, N-propyl. Dr. White likes N-propyl, not as much as isopropyl, which is why I said the wrong thing. 3 carbons, the N carbon is bonded to the ring or the chain. Now, there's another way you could have drawn this, and these are all correct. There are a lot of ways. But let's say you said that's 1, that's 2, and that's 3. Which one is correct? They're just both it. All you've done is rotate this 180 degrees to get to this. But either way, and there are other ones you could have written also. Let's do one more. In case you can't read it, it's 1-tert-butyl, 2-methyl, cyclopentene. Why don't you draw this one? 1-tert-butyl, 2-methyl cyclopentene. Doesn't it feel good? You can do organic chemistry. Everybody go like this. By the way, in a classroom, I do the same thing. I can be obnoxious online or in a classroom. All right, looks like the last carbon has gone down. Anybody need any more time? Going once, twice. All right, let's do this. How do you decode this? You start from the right and move left. ENE ending, double bond. Ooh, cyclo, ring. If this were ANE, cyclopentane, that's a ring with 5 carbons. And here I have it. Now, ENE double bond, I'm going to put it here. You could put it between any 2 carbons. On carbon 2, I have a methyl group. On carbon 1, I have a T-butyl group. So I could make this carbon 1 and run out of room. Hold on. By the way, this sometimes happens on a whiteboard in the school too. And Dr. White is having a good ring drawing day. Yay. I have my T-butyl group, 4 carbons, 3 attached to the center carbon, methyl, 1 carbon, put my hydrogens in. Now you could have also drawn it this way, which is all you're doing is flipping it. Remember, there's 4 bonds to carbon. So that's how I know how many, and that's how you do it. And that's nomenclature double bonds. Let's do triple bonds, and then we can get into the juicy stuff, reactions. Dr. White loves reactions. That's why I got my PhD in. Now, if we go back to the beginning, you'll see the ending YNE is used to designate a carbon-carbon triple bond. Forget about it, I won't put any 2 triple bonds, which would be diene. And still the longest chain, you find that and name it, and let's go do some. All right, let's look at the following molecule. Now, because the triple bond, which you should know, has 2 pi bonds and 1 sigma bond, it's linear. The bond angle is 180 degrees. It's straight like a pencil or a pen, And you don't have to worry about cis or trans. How many carbons in the longest chain with the triple bond? Again, when you look at an organic molecule, look for what's different. What's not a single bond, what's not carbon or hydrogen. 1, 2, 3, 4, 5. That was an alkane. That would be pentane. But it's a triple bond, it's an alkyne. And therefore drop the ANE and put in YNE. And like the double bond, you have to indicate what's the carbon of one of the carbons of the triple bond that's closest to the end of the molecule. If it's a chain, here 1, 2, so this is 2 pentine. If you have alkyl groups the same way, just number them and put those. So let's have you have some fun. And what would be the IUPAC name, 3 points each, of that molecule? Go. Isn't it nice Dr. White shares the fun? In about a week or two, you'll probably might think this is fun. As I've said it enough times, it works. Anybody else need more time? All right, let's do this. When you look at an organic molecule, look for what's different. What's not a carbon-carbon single? Oh, a triple bond. And therefore, this is an alkyne. How many carbons in the longest chain with both carbons a triple bond? Don't know. 1, 2, 3, 4, 5, 6, 7. And therefore, it's heptane, but since it's a triple bond, you drop the INE ending, put in YNE, heptyne. Now, which carbon of the triple bond, as they get the lowest numbers, is close to the end? If I start this way, it's 1, 2, 3. If I go the other way, 1, 2, 3, 4. So which is smaller? And you got to use your high-level math skills for my class. Remember, I will not allow you to use any electronic device on a test. Which is smaller, 3 or 4? Time's up. Hopefully you pick 3. So this is 3 heptyne. Oh, let's do another one. All right, again, what's the IUPAC name of this molecule? Let's see if you're up to the challenge. I think you are. Aren't you glad I'm not teaching this where here's the molecule, here's how you name it, and I'll learn it on your own? That's not right. I think the last letters just went down so I can get to work. All right, let's take a look at this. How do you know what to name it? You look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen. Oh, a triple bond. And that's an alkyne. This you don't have to put down in the test, but it's a triple bond. How many carbons are in the longest chain with both carbons of triple bond? I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's one chain. Another chain would be also 10. And then 1, 2, 3, 4, 5, 6, 7. So the longest chain with both carbons of the triple bond is 10. 10 is decane. Drop the A and E from decane, and it's a triple bond, and use Y and E, decyne. Now, which is the lowest number that the lead carbon of the triple bond is closest to the end? This side is 4. I go this side, be 1, 2, 3, 4, 5, 6. And now you have to use your high-level math skills, which is smaller, 6 or 4. And time's up. Hopefully all pick 4. So it's 4 decyne. Now you don't have cis or trans. So am I done? No. Oops. Eh. When I say 4 decyne, that's spoken for. Oh, look what's left over, a methyl group. No, 2 methyl groups. How do we show that? 2 is di, 3, 2 is di, 3 is tri. So this would be dimethyl. Now, that ran out of room, sorry, but you guys are worth it. Didn't run out of room. Now, there are 2 of them, so it's dimethyl. Now, because there are 2, you need 2 numbers. This methyl group is on carbon 3. This methyl group is on 6. So this would be 2, 6, oh, very long dash there, 2, 6 dimethyl, 4 decyne. Say that 5 times quickly. No, you don't have to. And that's how you do one part. Now let's do the other. Here's the name, draw the structure. I'll hold that there for a second in case you're writing it down. Oh, I forgot to warn you. Dr. White has the fastest mouse wheel finger this side of the Mississippi and the other side. If I scroll down too quickly where you're writing something down, say, hey, wait, don't use your microphone. I might miss it if you put it in the chat. Could you scroll back? And the answer will always be yes. All right, Now, the other type of nomenclature question or skill is, here's the name, draw the structure. And how would you draw 2-pentyne? Well, I think you're getting the hang of this. You start from the right and move left. Y on the ending now tells you triple bond. And if this were ANE, that would be pentane, 5 carbons. So here we have 5 carbons. Remember, you can't have sister trans and triple bond. I call this carbon 1, this is 2. I have my triple bond, and now I know there's 4 bonds to carbon. And I can put in my hydrogens. Your turn to have some fun too. Wait, let me go back. I see people still writing. Everybody caught up? Good. And why don't you try this one? Draw the structure for 3-No-9. Say that 5 times quick. No, you don't have to. For those who are having a late lunch, I hope you're enjoying it. Watch out, Dr. White is nosy. All right, I think everybody's done. Let's do it. How do you do this? You always decode an organic chemistry name by moving from the right and going left. Later in the semester, I'll teach you the chemical difference between your right and left hands. But for now, I hope you all know right to left. And if I look at here, I see Y on the ending, triple bond. If this were ANE, none, 9 carbons. Now, 1, 2, 3, you could have started from this side, but most of you are going to start from that side. I have my triple bond starting at carbon number 3. And I know there are 4 bonds to carbon, and that's how I draw it. Oh, let's do one more. Let's have some real fun here. And why don't you draw 5-ethyl 2-decyne? Have fun. And I know you will. Remember, smiling is permitted in my class, always. For those of you writing, years ago, when I first started teaching this, I used to write these problems on the board, and have students go up on the board and do them. Until I found out students would rather pull out their teeth with pliers than go to the board. And I was wondering, why am I making these people miserable? So I stopped doing that. I guess I could put you in private chat rooms to make you go to the board, but nah. All right, anybody need more time? I'm listening. All right, let's do it. How do you decode this to know what to draw? Start from the right, move left. YNE ending, triple bond. If this were ANE, decane, 10 carbons. I better get to work. Now, where's the triple bond? Carbon 2. So if I do this, you could have started from this end, but most of you won't. So I'll do what you do. Triple bond. But am I done? No, I have an ethyl group, 2 carbons on carbon 5. 3, 4, 5. It doesn't matter which way you draw this carbon on this side or this side. I'm going to do it this. And now I know there are 4 bonds to carbon. And this is 5 ethyl. That's my ethyl group. 2 on carbon 2, it starts my triple bond, 2 decene. There are 10 carbons, if I counted correctly, and I think I did. And that's how you do the nomenclature for triple bonds. There's some people writing it down in case you get. Remember, if you're having trouble now and you're just new. So you'll have practice, because I have practice problems for this. We'll do later on. You should be working on this week or next week. And any questions on this? Any questions on nomenclature? Going once, twice, 3 times. No questions. Let's continue on. I see a question. Question for alkynes, can you use sister trans? And the answer is no. They're linear, straight across. Because it's trigonal planar for double bond, you can have sister trans, but a double bond is like my pen here, it's straight, a triple bond, straight across. So no, you can't have sister trans, and that's a good question. Thank you for asking that. Did the clicking come back, or is it gone now? Oh, I was looking at an old one. All right, that's the other thing. I got to look at the timestamp. All right. first of all, let me remind all of you, there are 4 bonds to carbon. 4, 4, 4. By the way, notice I'm in my ninja uniform, except I didn't bring my nunchucks along. Yes, Dr. White knows how to use nunchucks. I have 6 pair, 12 total. I was into it younger, and yes, I know how to use them quite well. Twice they saved my life long ago when I lived in Chicago. But anyways, finally, nomenclature is important, but that's not the exciting part of organic chemistry. Now we're going to get into the good stuff. And let's talk about reactions of alkenes. Now, alkenes undergo what's called an addition reaction. And addition reactions is where you break the pi bond. This is something you should know. A double bond is made up of a single sigma bond, which is like a single bond. The second part, pi bonds. Pi bonds you break easy, almost rarely other than combustion. When you burn something, do you break a sigma bond? So the new thing I'm going to be teaching you now, do you break carbon-carbon single bonds? No. Do you break carbon-carbon single bonds? No. Just like there's 4 bonds to carbon, do you break carbon-carbon single bonds? No. And those 2 things will be your friend. All right, Paige, after class today, I'll tell the nunchuck story. You got to wait because I don't want to take up, I won't even charge extra. It's a good story too. Actually, there are 2 of them. But you didn't learn, think about all the things you're going to learn this semester. All right, so what's an addition reaction? Addition reaction, let me quickly ask, thumbs up people. Can you see the chemical reaction with A and B on there? Thank you. Now this, you don't have to write down, but an addition reaction, you react something with a double bond. Now I have to teach you something else. Notice here, I have R over here, R. R in organic chemistry is just like if I had this in math and relax, we're not, x plus y equals 100. These are called variables. In organic chemistry, R means anything with carbons and hydrogens. You can have 1, you can have 5, you can have 1,000,000. But in a molecule, wherever you see the double bond and you add something to it, we'll learn what A and B can be. You break the pi bond and 1 carbon, by the way, there should be a carbon here. Every bend in the line is carbon. I got lazy and missed that. 1 carbon gets A, 1 gets B. And this is an addition reaction. Now it's time to learn your first real chemical reaction. And by the way, note in this class, carbon-carbon single bonds are almost never broken except for combustion. And I don't teach reactions of ozonolysis anymore. Finally, hydrogenation. I'm going to be naming different reactions. You do not have to know the name of the reactions, but I'll use them because I do. And excuse me, hydrogenation is the addition of hydrogen to an alkene, double bond. Now you need a catalyst. A catalyst is something that makes something go quicker, but is not consumed in the reaction. In this case, it's either platinum, palladium, or nickel. If you have any molecule with a double bond reacted with hydrogen and a catalyst, you break the pi bond and each carbon of the double bond gives a hydrogen. Let's look at another way of writing this same thing. This is another way of saying any molecule with a double bond If I react it with hydrogen and a catalyst can be platinum, palladium, or nickel. Now, there's something I should show you. Let's go to a different color. I don't know if I mentioned this, but I think I might have. Organic chemists can write a reaction this way. This tells you A and B react to make C. Or we can write it this way. A and B react to make C. And that's the same thing here, except I also have a third thing I put in, so I put it underneath the line. And what happens here is you break the pi bond, change color to carbons too. Now let's get this right. Break the pi bond, the sigma bond you don't, and each carbon gets a hydrogen. Now, on a test, I will never ever ask you what's a general reaction, but you need to learn these either this way, or usually I'll write it again, the condensed or the real simple way, this way. Let's show you what I will do on a test, or in real life, what I need to know as an organic chemist. Since I've been switching around, I better check my thumbs up, people. Everybody see 3 points each? Thank you. And I should tell you, organic chemists are very biased. Things that aren't organic molecules, for the most part, when we're just doing reactions on paper, we don't care about. So that's why give the organic product or products for the following. Let's do our first real reaction. Oh, I'm so excited. And the question is, what's the product for it? Well, how do you do this? Well, first thing, you look at the molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Because that's where the action is, double bond. What am I reacting with? Hydrogen. And what's nickel? A catalyst. Remember, the catalyst here can be nickel, platinum, or palladium. In industry, we use nickel because it's cheaper. In pharmaceutical, they can get away with platinum or palladium. And what happens? You break the pi bond. Remember, this is one pi bond and one sigma bond. And each carbon gets a hydrogen. Now, notice here I have a sigma bond, here I have a sigma and a pi. So immediately I know I start out with 1, 2, 3 carbons. I better end up with 1, 2, 3 carbons because you don't break carbon-carbon single bonds. No. Once I started teaching that years ago, when I was teaching organic, the scores on the test zoomed up because people do the weirdest wrong things. Now, notice I had the double bond, pi bond there, but it's not there. There's only one line here where there are 2 lines there. I broke the pi bond. And what does my general reaction tell me? Each carbon of the double bond gets a hydrogen. I know there are 4 bonds to carbon. So I can put in the remainder like this. Now, you can write the molecule this way, or you can rewrite it CH3. Notice this carbon has 1, 2 hydrogens, CH2, CH3 on the last one, 2 plus 1. Now, on a test, I'd recommend you do this because it's one less step. If you want to do this, feel free to, but I won't care if you do it either way. And then I tell you, I'm this close to the person who grades the test, me. And therefore you can do it either way. Either way I'm familiar with. I'd recommend the top way because it's easier for you, one less step to make a mistake. All right, let's look again. What did I do? Look for what's different. Double bond. Looked at my reagents, wrote it down. I memorized. This is something you got to start memorizing. Flashcards don't work as good as writing it down and saying double bond, hydrogen catalyst, here's your catalyst. You break the pi bond, do that, and say don't break carbon-carbon single bonds. I started with 3 carbons, ended up with 3 carbons, and each carbon got a hydrogen. Now, sometimes when I'm running out of room on a board or whiteboard, I'll do an arrow like this. And it's your turn. Give the organic product or products through the following. Now we're getting into the good stuff. I see people still putting down hydrogen. So those who finish first, please be patient. Remind yourself how many bonds to carbon. All right, I think everybody's done. Let's do this. So how do you do this? You look at what is different. What's not a carbon-carbon single bond or carbon-hydrogen? Oh, a double bond. What am I reacting it with? Hydrogen, and what's platinum? A catalyst. And what can those catalysts be? Platinum, palladium, or nickel. And what happens? You break the pi bond. Remember, double bond is 1 pi bond, 1 sigma bond. And each carbon of the double bond, these 2 carbons, get a hydrogen. Now, you break carbon-carbon single bonds. Watch. No, you don't. Therefore, how many carbons do I have here? 1, 2, 3, 4, 5. I better end up with 5. Which carbons are those of the double bond? These two, which are these two. And what my general reaction shows me, that each one gets a hydrogen, which I did. And now I know there are 4 bonds to carbon. And I can put them in. I did. Now, if you wanted to make this CH2 and this CH2, that's fine, but this is easier for you. And I'm trying to help you get the best grade possible. So there you go. Oh, let's do one more. And why don't you try this one? What would be the product or products for a following reaction? Give the organic product or products for the following reaction 3 points each. Give me a thumbs up when you're done. All right, I think everybody's done. Wait, no. See, someone's still writing hydrogens, which is allowed. All right, I think the last hydrogen just went down. Let's do this. Now, this is a chemistry instructor's favorite trick on a test. Put a big scary molecule, and that's a big scary molecule if you don't know organic chemistry, and you put this on a test, and students all of a sudden go, eek. Well, hopefully you don't go eek, but they just freak out. Oh, what do I do? Well, no. If you've learned organic chemistry the way I'm teaching you, you won't freak out, because what do you do when you look at this? You look for what's different. And it's sort of small, I apologize. But what do we have that's different? You look through the whole molecule, all I see is a double bond. Everything else comes along for the ride, because that's the only place something's going to happen. Double bond. What am I reacting it with? Hydrogen. And a catalyst. The catalyst can be nickel, platinum, or palladium. You break the pi bond, and each carbon of the double bond gets a hydrogen. Remember, that's 1 pi bond and 1 sigma bond. Now, do you break carbon-carbon single bonds? No, you don't. I do that in the classroom too. No, you don't. So, notice we have here 1, 2, 3, 4, 5, 6 across. Methyl's here and methyl here. So I'm going to have 6 across. I have 2 methyls here. I have a methyl here. Why? Because you don't break carbon-carbon single bonds. Now, here are my 2 carbons of double bond. My general reaction shows me you break the pi bond, which I did, and each atom, carbon atom of the double bond gets a hydrogen. I can do that. And now I know there are 4 bonds to carbon. And I'm done. Oh, I apologize. I went a whole minute over. First of all, for those of you writing it down, let me check. I'll go a whole minute and 30 seconds. Anyways, you want to stick around for the nunchuck story. All right. Again, this is the way instructors scare students. I'm out of time. All right, first of all, remember on Wednesday after class, I will be teaching, for those who want to stick around, how to eliminate test anxiety. On Wednesday, since we're not really having a lab, I'm going to go till about 10 to 2 or quarter to 2. No, I take that back. Hold on. 2:45, because I still want to pick up some time, because next Monday is Labor Day. No Dr. White, no class. But anyways, with that, for those of you who are leaving, I'll say, Gang gesund, goodbye.